Okay, let's dive into something that honestly sounds like it's pulled straight from science fiction. The incredibly deep link between artificial intelligence and the fundamental physics that runs our entire universe.
So, this whole thing really kicked into high gear when John Hopfield and Geoffrey Hinton, who are basically the godfathers of AI, got a Nobel Prize. But it wasn't for computer science, it was for physics.
And yeah, that's the big question, right? It just seems odd. I mean, what on earth do algorithms that can chat with us have to do with the laws that govern atoms and galaxies? Well, as you're about to see, the answer is this incredible story that weaves together magnets, memory, and the very fabric of reality itself.
To really get this, we've got to go back in time, way back. And we're not starting in some Silicon Valley lab. Nope, we're starting in 1920s Germany with a really simple question. How does a magnet actually work?
So our story starts all the way back in 1920 with a physics problem given to a student. Then it jumps ahead to 1982, right at the dawn of modern computing, before taking two more huge leaps in 1995 and 2020 that bring us right to the absolute cutting edge.
Right, so in 1920, this student, Ernst Ising, had to figure out how to model a magnet, and he came up with a really simple idea. Just imagine all the atoms in a piece of iron are on a neat little grid. Each atom has a tiny magnetic field, which he called a spin, and it can either point up or down. That's it. It's a super simplified, almost cartoonish model of a magnet.
Now, here is the absolute key principle from physics you need to know. Nature is fundamentally lazy. I mean, everything in the universe is always trying to settle into its lowest possible energy state. For these little spins, it just takes less energy for them to line up with their neighbors. So over time, that's exactly what they do. They align.
You know, the best way to picture this is to think of a marble rolling around on a big, hilly landscape. The marble's position is like the arrangement of all the spins, and its height represents the energy. That marble is naturally going to roll downhill and settle in the bottom of a valley, right? Well, those valleys are the stable, lowest energy states. They're the organized patterns.
Okay, now let's fast forward about 60 years to 1982. A physicist, John Hopfield, is looking at this old, simple model of magnets and has this just incredible aha moment. He thinks, what if you could build an artificial brain that works on the exact same principle?
Hopfield basically did a find and replace on the physics. Instead of atoms with spins, he had artificial neurons that were either on or off, active or inactive. The magnetic force that aligned the atoms became synaptic weights, basically the connections that tell neurons whether to influence each other. And here's the genius part, that stable, low-energy state was no longer a magnet, it was a memory.
So how does it learn? Well, this is where it gets really cool. You can essentially sculpt that energy landscape we were talking about. By changing the strength of the connections between the neurons, you can literally dig a valley that corresponds to a pattern you want it to remember, like, say, the image of a cat.
And this is the brilliant result. You can show the network a blurry, incomplete picture of a cat, which is like putting the marble on the side of that cat valley. Then you just let it go. The network evolves on its own, the marble rolls downhill, and it settles right at the bottom, into the perfect stored memory of the cat. This was the birth of a machine that could actually learn from data.
But, believe it or not, that's really only half the story. The connection between AI and physics gets way, way deeper and, frankly, a little bit weird. It stops being an analogy and starts becoming a shared mathematical identity.
So try to think about a neural network in a different way. Don't picture a web of neurons. Instead, think of it as a mathematical field, kind of like a weather map that has a temperature for every single point, or a gravitational field. It just takes an input and assigns a value to it.
Now here's where we get into a pretty mind-bending thought experiment. What would happen if you just kept adding more and more neurons to your network? You just make it wider and wider, all the way to infinity.
You'd probably expect it to become pure chaos, right? Just a mess of random noise. But something absolutely amazing happens. Out of all that infinite complexity, a very simple, very predictable pattern starts to emerge.
And what is that pattern? It's the good old bell curve, what mathematicians call a Gaussian distribution. It's this simple, elegant shape you see everywhere in nature. And it turns out that pretty much any neural network, when you imagine it being infinitely wide, behaves in this incredibly simple and predictable way.
And get this wasn't some new discovery. This shocking link was actually figured out way back in 1995 by a guy named Radford Neal, who just so happened to be a student of Geoffrey Hinton, the same guy who just won the Nobel.
Okay, so infinitely wide neural nets make a bell curve. That's kind of neat, I guess. But why is that a Nobel Prize in physics level discovery? Well, because it turns out that something else in the universe behaves in exactly the same way: quantum fields.
This is it. This is the heart of the whole thing. The absolute simplest model of a quantum field, which is how physicists describe all particles and forces, also fluctuates randomly according to a perfect Gaussian distribution. An infinitely wide neural network and the basic fabric of reality speak the exact same mathematical language. It's unbelievable.
And the connection gets even crazier. I mean, in the real world, our networks aren't infinite, and particles in the universe definitely interact with each other. In both cases, you have to make little corrections to that perfect bell curve. And it turns out, the math you use for the AI corrections is a direct analog to the math physicists use, things like Feynman diagrams, to describe how real particles bump into each other. Even the imperfections match up.
So this is so much more than just a cool coincidence. This deep mathematical connection means we have this powerful two-way street where AI can help physics and physics can help AI solve their biggest, gnarliest problems.
And I mean, AI is already changing the game for physics. It's doing incredible things like cleaning up the super faint signals from colliding black holes, mapping the invisible dark matter that holds galaxies together, or simulating the insane behavior of quarks. These are problems that would completely crush our best supercomputers.
And the street goes both ways. Physics is giving us a whole new toolkit to finally understand AI. For years, we've talked about AI as this unexplainable black box. But now, using ideas like energy landscapes and quantum field theory, we can actually translate what it's doing into a language we understand. We're getting a real peek under the hood.
So why a Nobel in physics for AI? Because it turns out the fundamental rules of machine learning and the fundamental rules of the cosmos are just profoundly connected. And that leaves us with this incredible, mind-bending question. If AI and the universe really do speak the same language, what other secrets are they going to unlock when they start talking to each other?